Section 4.8 is it's called complex numbers, but we don't get into complex numbers until after we learn about imaginary numbers. Complex numbers actually are imaginary numbers, so it's easier to start off by learning about imaginary numbers before you get into complex numbers. Find the square root of each of these numbers. I just want to review square root math here a little bit for you officially so that we remember how to do it, because we need to know how to do it when we start working with imaginary numbers. So what is the square root of 16? 4. What is the square root of 25? It's 5. We're not including the plus or minus here because it's not an equation. We didn't take the square root of both sides of an equation with a variable involved. So the square root of 16 is just 4. What about the square root of 40? This has to be simplified. To simplify a square root, you have to find the biggest perfect square that's a factor of the number you're looking at. 4 times 10. 4 is the biggest perfect square that goes into 40. So 4 times 10 is what we come up with. And now the square root of 4 times 10 can be split into the square root of 4 times the square root of 10. The square root of 4 I can take, it's 2. The square root of 10 I cannot take, so I leave it the square root of 10. So the square root of 40 simplifies to 2 root 10. How about the square root of 48? The biggest perfect square that's a factor of 48 is 16 times 3. So this splits into the square root of 16 times 3, because 16 times 3 is 48. And then we can split that into 2 little square roots, the square root of 16 times the square root of 3. The square root of 16 is 4. Once you take the square root symbol's gone. 4 root 3 is the answer. I've taken the square root of 16, it's 4, so the square root symbol's gone. It just so happens that 4 is also a perfect square. Don't let that confuse you, though. How about the square root of 57? 57's prime, actually. 9 times what? 9 times nothing. 6 times 9 is 54, but it doesn't work. 19 is not a perfect square either. 57 is actually not prime, 19 times 3. But 19 is not a perfect square, neither is 3. So this is already simplified. Not prime. It's already simplified. The square root of 57 is just the square root of 57. It does not simplify. No, it is not no solution. It's not prime, it's just the square root of 57. How about the square root of 96? First of all, is 96 a perfect square? No, it's not. 100 is, 81 is, but not 96. Does it simplify? To what? What's the biggest perfect square that goes into 96? 16 times what? 16 times 6 is 96? I don't know. If you don't know, then you can do this. You're always welcome to go back to this method right here of factoring it completely. So the smallest prime number that goes into 96 is 2. 2 times what gives me 96? 48. Okay, we still have a factor of 2 that goes into 48, which gives me, and then another factor of 2, which gives me, and then another factor of 2, so 6, and then another factor of 2 for 3. Now once we're here, we just circle all our pairs. We have a pair of 2's, we have another pair of 2's. That's it for the pairs of 2's. Then you multiply all those numbers back together. 2 times 2 times 2 times 2 is 16 times 6. So this splits into the square root of 16 times 6. You were right. And then the square root of 16 is 4 root 6. Notice this time I didn't write the step where I split them into 2. That's perfectly fine. If you understand that from here to here we're splitting this into 2, then you can go straight from here to here. That's square root math. That's how you simplify roots. And you're expected to do it all over this section and pretty much from now on. Questions on that? Okay, now solve for x. Same idea going on here. If I solve that first one for x, what do I need to do? Take the square root of both sides. And when I do, I get x equals, not 10, plus or minus 10. Now we have to include the plus or minus because we're taking the square root of both sides of an equation. 10 squared is 100. Negative 10 squared is also 100. How about the next one? What do we do? Square root both sides? Okay, so on the left now we have x. On the right we have plus or minus the square root of 50. That's not good enough. The square root of 50 simplifies. What's the biggest perfect square? That's a factor of 50. 25 times 2, yeah. So we're going to have x equals the plus or minus the square root of 25 times 2. And then the square root of 25 is 5. So I have x equals plus or minus 5 root 2. On the next one, what should I do? Move the 18 over. Get x squared by itself, and then I can use the square root property. So x squared equals positive 18. Now what? Square root both sides, and I get x equals what? No. Plus or minus the square root of 18, which is x equals plus or minus the square root of 9 times 2. And then the square root of 9 is 3. So I write x equals plus or minus 3 square root 2. For the next one, what should I do? Get x squared by itself. So now we have x squared equals positive 56. Now what? Square root both sides, x equals plus or minus square root 56. Is there a perfect square that goes into 56? So our perfect squares are 4, 9, 16, 25, 36. 36 doesn't work. 25 doesn't work. 4 does though. 4 times 14. So this becomes x equals plus or minus square root 4 times 14. Which will simplify to x equals plus or minus what? 2 root 14. How about the last one? X squared equals negative 9. We move the 9 over. Now what? Take the square root of both sides, and now you have x equals plus or minus the square root of a negative number. And we can't take the square root of a negative number. Because remember, the square root means I'm looking for two numbers, or sorry, not two numbers, I'm looking for one number that times itself will give you negative 9. And there is no one number that does that. What you have sitting in front of you is an imaginary number. The square root of a negative number can't be found. It's imaginary. Although I'm looking at it right here, we call it an imaginary number. It doesn't exist. There's no number that does that. But we can work around it, and that's the whole point of this section. So since we can't take the square root of a negative number, what do? Square root of a negative number doesn't exist. In other words, the answer is imaginary. So that's why we call these imaginary numbers. We can work around that square root of a negative number, though. So we can work with imaginary numbers. To do that, we use the letter I. What we're going to do is define I equals the square root of negative 1. It's going to act like a variable in some ways. But it's not a variable. I is equal to, I is a number. I is the square root of negative 1. It's an imaginary number. It's our most basic imaginary number. So now if I want to find the square root of all of these numbers that are negative, I can, because of the fact that I is equal to the square root of negative 1. So if I find the square root of negative 1, what do I get? It's I. For the square root of negative 16 now, what I'm going to do is I'm going to rewrite this as the square root of 16 times negative 1. 16 times negative 1 is negative 16. And now what I can do is split that into the square root of 16 times the square root of negative 1. And the square root of 16 is 4. And the square root of negative 1 is I. So 4i is the answer. The square root of negative 25 will split into the square root of...
Do we have to go through all those?
No, you don't. But it splits into the square root of 25 times negative 1. And then the square root of 25 times the square root of negative 1. The square root of 25 is 5. The square root of negative 1 is I. So the answer is 5i. And this is how we get around working with imaginary numbers. How about the square root of negative 40? So what you're going to do, yes, you're taking the square root of that. You're going to split this into the biggest perfect square that goes into 40, which is 4 times 10 times negative 1. And now the square root of 4 is 2. The square root of 10 I cannot do, so I leave it. The square root of negative 1 is I. So I have a couple ways I can write that. I can write 2 root 10i, or I can write 2i root 10. I take either, but I prefer having the I before the square root. Yeah, the reason is if I write this all close together, it's very easy to confuse where that I is. It could be under the square root, it could be outside the square root. And I think it just makes it easier if you write the I here. If you look at the answers in the back of the book, a lot of the time they're going to write it like this. They might put a dot there to show that it's times I. It really doesn't matter to me. This is how I learned how to do it though, so that's how I prefer it. But if you guys write it the other way, it's perfectly fine. And you'll also see me write it this way as well, so... They write it which way? The way I have circled? Okay, perfect. Square root of negative 48, what do I do?
3 times 16 times negative 1.
So the square root of 16 times 3 times negative 1. 4i root 3. And the square root of negative 57? It's not prime, it just can't be simplified. There you go. And the square root of negative 96? Remember that splits into 4 times 4, no, sorry. 16 times 6 times negative 1. The square root of 16 is 4i root 6. This fun little page is actually illustrating a very, very important concept when we come to dealing with imaginary numbers. You see these giant exponents here, but you'll see in a minute that there's a reason why I'm showing you this. What is I to the first power? It's just I. We know that I is the square root of negative 1. Okay? I to the first power is just I. Well, what is I squared? I squared is I times I, right? Well, I is the square root of negative 1, though. So I have the square root of negative 1 times the square root of negative 1, basically. Right? Which I can rewrite as the square root of negative 1 being squared. Do you agree? So it's just negative 1. If I square something that's being square rooted, the square and the square root go away. And I'm left with whatever it was that I was squaring and square rooting. In this case, negative 1. So therefore, I squared equals negative 1. I to the third power can be rewritten as I squared times I to the first. Do you agree? Okay. Well, I squared is what? Negative 1. So I have negative 1 times I, which is negative 1i, or just negative I. I to the fourth power can be rewritten as I squared times I squared. And I squared is negative 1 times negative 1, which is 1. So I to the first power is I. I squared is negative 1. I to the third power is negative I. I to the fourth power is 1. So let's continue. If I to the fourth power is 1, then I to the fifth power can be rewritten as I to the fourth times I to the first. And I to the first is, this is 1 times I, which is I. I to the sixth can be rewritten as I to the fourth times I, what? Squared. I to the fourth is 1 times I squared, which is, I squared is negative 1. I to the seventh can be rewritten as I to the fourth times I to the third. I to the fourth is 1 times I to the third, which is negative I. I to the eighth can be rewritten as I to the fourth times I to the fourth. I to the fourth is 1 times I to the fourth, which is also 1, so we get 1 times 1 is 1. Now that I know that I to the eighth is 1, I can split I to the ninth into what? I to the eighth times I, which is I. I to the 10th can split into I to the 8th times I squared, which is I to the 8th is 1. I squared is negative 1, so we get I to the 11th splits into I to the 8th is 1. I to the 3rd is negative I. And I to the 12th probably is going to become 1. Do you see the pattern?
Every fourth one is 1, every third one is negative I.
Look at the way I have these arranged.
5 and 9 are I, 6 and 10 are negative 1.
Look at the columns. So what I want to do is, it says in your own words, right, how to find I to the nth power. Use the pattern to find I to the 31st. We need to identify the pattern here first, okay? Obviously in each column we have I to the first is just I to the second is negative 1, I to the third is negative I to the fourth is 1. In each sequential row, what I did was I took this power right here and split what I was looking at into that power times what's left over. In this one, I took I to the 8th times what's left over all the way through. So on my next row, I'd take I to the what? 12th. And the next row would be I to the... What's going on with these I's right here? They are multiples of 4. That's right. So what you're going to do is I to the any power that's a multiple of 4 is going to give you 1. So you want to find, and this is your own words right here, it's my words right now, but make it your own words as you write it down. You want to find the biggest power that's divisible by 4 that's less than the exponent you're looking at. And then what's left over will give you either this, this, or this. So for I to the 31st power, what is the biggest multiple of 4 that's less than that exponent? 28. So this would split into I to the 28th power times I to the what? I to the third. I to the 28th becomes 1 times I to the third, and I to the third is negative I. Notice that when you're simplifying these, in any of these cases, you either wind up with I or negative I, or you wind up with 1 or negative 1. There's never an exponent on I. If you have an exponent on I, it can be simplified. So you'll have to remember that. That's an important rule. But write down in your own words how to find I to the nth. This is on quizzes and tests and final exams, so it's worth knowing. Now that we know how to work with I, we can start to work with imaginary numbers and start to get into complex numbers as well. So if I have negative 5i times negative 4i, I can simplify that. If that was negative 5x times negative 4x, what would you get? Positive 20x squared. The same thing happens with I. You can treat it like a variable. So the negative 5 times negative 4 is positive 20. I times I is I squared. But I squared is negative 1. So this is actually 20 times negative 1, which is negative 20. There's our answer. The square root of negative 15 times the square root of negative 6. Can I multiply those two numbers together? Yes, I can. If you remember the property where we have the square root of a times b equals little square root a, little square root b, this works both ways. This is what I'm looking at right here. I can go the other way and put both of those numbers together under the square root. So that gives me the square root of negative 15 times the negative 6, which gives me the square root of negative 15 times negative 6, which is positive 90. Is that my answer? I got to simplify that square root. What's the biggest perfect square that goes into 90? 9 times 10. So this becomes the square root of 9 times 10, which gives me an answer of 3 root 10. Notice on this one that is this imaginary or real, the square root of negative 15? It's imaginary. You can't take the square root of a negative number. Is this real or imaginary, the square root of negative 6? Imaginary. I multiplied those together and I wound up with real or imaginary? Real. So it's possible to wind up with real numbers even though you were working with imaginary numbers. How about this one? 12i squared. Now I squared is negative 1. So this is actually 12 times negative 1, which is negative 12. Again, I had two imaginary numbers. I multiplied them together, and I wound up with a real number. It's not always going to happen, but it can. How about the square root of negative 3 times the square root of 6? What's the first thing I should do? So we have the square root of, which is negative 18. Now what? So the biggest perfect square that goes into 18 is 9 times 2. So this becomes the square root of 9 times 2 times negative 1. So I'm going to write my answer is 3i root 2. And the last one, I to the 29th power. What do I do there? So the biggest multiple that's less than 29 is 28. So I'm going to split this into I to the 28th times I to the first. I to the 28th becomes 1. So I have 1 times I, which is I. Same ideas going on in these bottom problems. Now we have equations to solve. We can solve equations now that we know how to work with imaginary numbers. So if I want to solve this equation, what do? X squared equals negative 4, and then we square root both sides, and we get x equals plus or minus 2i. So now you actually can solve these equations using imaginary numbers. How about the next one? What should we do? Subtract 256 from both sides. 4x squared equals negative 256. Now what? Divide everything by 4 and you get x squared equals negative what? 64. Now what? Square root both sides and you get X equals what?
plus or minus 8i.
8i.
Why is there an I at the end?
Why is there an I at the end? I have the square root of a negative 64. Anytime you have the square root of a negative number, you're going to have an I. And the last one, what do we do?
2x squared.
Move the 100 over. 2x squared equals negative 100. And then,
5 by 2.
okay, x squared equals
50.
negative 50.
Plus or minus 8.
We didn't take the square root of both sides yet. Now we can take the square root of both sides and we get x equals, let's write this one down, plus or minus the square root of, we need a biggest perfect square that goes into 50, which is 25 times 2 times negative 1. Now we simplify that, x equals plus or minus 5 I root 2. And again, if you wrote that I at the end, I wouldn't care too much. It's just that we prefer to have the I in the middle so that we don't get confused.
Got a soapbox?
So that was the introduction for imaginary numbers. Now we're getting into the more important and more relevant complex numbers. Complex numbers have a real part and an imaginary part as one number. It looks like it's two different numbers or two different terms of what maybe a polynomial or something, and we can work with them like that, but it is actually one number. A complex number has a real part and an imaginary part, both. Actually, every single number that you've ever worked with ever in your entire lives had a real part and an imaginary part to it. It's just that the imaginary part was 0. For example, the number 3 plus 4i, this right here, is a complex number. It has a real part and it has an imaginary part. Those terms can't be combined, just like combining like terms when you're dealing with regular variables. Can't be combined. You leave them as is. But that is one number sitting right there, 3 plus 4i. The real part would be the 3. The imaginary part would be the 4i. In general, a complex number looks like this, a plus bi, where the a is the real part and the b is the imaginary part. I don't want to write b, I want to write imaginary. That guy right there is the imaginary part. There's a real part and imaginary part to every single number. We can add, subtract, multiply, and divide them just like we do with any polynomial. With any polynomial is the key here. Treat them like polynomials, like variables. When you do that, then you can multiply and divide and add and subtract them. Basically, you're just combining like terms. To add or subtract complex numbers, combine the real parts, combine the imaginary parts separately. Think combine like terms. That's all you got to do. So I need you to see this plus sign in between, this plus sign in between, this minus sign in between. There's addition or subtraction going on in between those complex numbers. Because of that addition and subtraction, we are just going to combine like terms. So on this first one, we have 5 plus 2, which is 7. Then we have the negative 7i plus the 4i, which gives me negative 3i. That's your answer. You're basically just combining like terms.
Oh, I see where this is going.
Yeah, I'm sure you do.
Oh.
It's not that bad. You actually are seeing the easier part of where it's going. You're talking FOIL, right? Yeah. For this one, we have the real parts combined. Negative 2 plus 1 gives me negative 1. Then we have 5i plus negative 7i, which gives me negative 2i. That's your answer. And the last one, notice that it's subtraction this time. So think to yourself, 4 minus negative 1, which becomes 4 plus 1, which is 5. And then we have 6i minus 6i, which is 0i, which reduces down to 0. 0 times anything is still 0, even if it's an imaginary number. So the answer here is just 5. It is possible to wind up with a real answer that has no imaginary part in it when you're doing these problems. That was addition and subtraction of complex numbers. Now we're going to do multiplying complex numbers. Follow the usual rules for multiplying polynomials. That means you're going to FOIL. You're doing the distributive property here. Don't forget I squared equals -1, so that when you're simplifying, you can simplify that as well. So simplify 2 minus 3i, this is one number, times 5 plus 2i, another number. They're complex numbers. You're going to simplify them by FOILing. So to FOIL, we get 10 plus 4i, that was this one, minus 15i, that was this one, minus 6i squared. So now we're going to combine like terms. We have the 10 here. We have 4i minus 15i, which is negative 11i. And then we have minus 6i squared, but I squared is -1. So that's negative 6 times -1, which is plus 6. And then we can combine like terms one more time. This becomes 16 minus 11i. Next one, what do we do? FOIL. How do I know that it's a FOIL? There's no sign in between. Good. Make sure you notice that sign. Okay, so I'm going to FOIL and I get 5 minus 1i, or just minus I, and then plus 20i, then I times -1. Sorry, I already did that. 4i times -i is, okay. What does -4i squared turn into? Positive 4. So now combine like terms. We have 5 sitting here, and this is basically positive 4 for a total of 9. Then combine these and you get, there's your answer. Okay, the last one we're going to FOIL again. And what do we get?
9 minus 59. Then you got 15i.
Good? Now, this turns into what? Positive 25. Combine like terms here and you get 0. It's gone. So you're left with 9 plus 25 for a total of 34 is your answer. Notice the bottom line here. Notice in the last example, the imaginary part of the solution disappeared. In every single example we've had so far, there's an imaginary left. Here, we didn't have one. What's special about that problem that maybe made the imaginary part disappear?
Plus 5i squared.
It's not 3 plus 5i squared. It's close to that, though. We have the 3, we have the 5i, but then we have a plus and a minus. Do you remember that pattern? That's that pattern. And I told you that this pattern is incredibly important a little bit later in the same chapter. It's here. This is why it's important. When you have a situation like this, where it's the same term, and then there's a plus and a minus like we have here, when you FOIL those back out, you wind up with this term squared, this term squared. Why did it become a plus here? Because of the I squared, that's right. So we're actually going to be working with this situation a lot in this section, and pretty much forever. So you need to know, these are called conjugates. Conjugates make the middle two terms in FOIL disappear. The O and the I go away. And you're left with just the F squared and the L squared being subtracted. We're going to be working with conjugates a lot. We are going to start this right now. We've done addition, subtraction, and multiplication now. Dividing complex numbers. This is how you do it. We're going to use complex conjugates. No, they don't. When you're dividing complex numbers, it gets tricky. This is definitely, of the four operations, the hardest of the four. But if you remember that complex conjugates, the conjugates make the imaginary parts disappear, then you can work with these. There's a rule, like you can't have a square root in the denominator. Remember, that's rude. You can't leave a square root in the denominator in your answer. You also can't have an imaginary number in the denominator of your answer. So that's also rude. So we are actually being very rude with all four of these problems. We have imaginary parts in each one of these denominators here. We have to get rid of those imaginary parts in order for this to be considered simplified. Okay? It's going to happen by doing a bunch of fancy ones and using conjugates. So I'm going to need a fancy one in this problem. I have to get rid of that I. Well, I know from earlier, if I multiply I times I, what do I get? I get -1. So if I multiply 5i times I, I'll get 5i squared, which gives me -5. The imaginary part is now gone from the denominator. So in this case, my fancy one is just I. But now I have to multiply that out. I have 5i times I, which becomes 5i squared. And I'm just going to be very formal here and write everything down. In my numerator, though, I'm going to have to distribute. That is an I times the number 4 plus I. I got to distribute there. So I get I times 4, which is 4I, and then I times I, which is plus I squared. So now we can simplify this. 4i can't be simplified, but I squared can be. It becomes -1. Divided by the 5i squared can be simplified. It becomes -5. Now the normal format for complex numbers is a plus bi. We want the imaginary part to be last, and we want it to be two separate terms. So I'm going to rewrite this a couple times. I have 4i minus 1 here, but the i's in the wrong spot. I need it to be over here. So I'm going to make this -1 plus 4i. That was a positive 4i, it's still a positive 4i. That was a -1, it's still a -1. Divided by the -5. That -5 is like a common denominator for the two numerators that you see. I can split that into two separate fractions. -1 over -5 plus 4i over -5. Now I have my two terms. I just need to reduce those fractions if I can. -1 divided by -5 becomes positive 1/5. And then -4 divided by -5 becomes -4/5. So I'm going to write minus 4/5 with the I off to the side. There's your answer. 1/5 is the real part. -4/5 I is the imaginary part. You're going to have to do it. The second one here, same idea. We have an imaginary part in the denominator. I got to get rid of the imaginary in the denominator, which means I need to multiply by a fancy one. The fancy one here is going to have to be a complex conjugate so that the imaginary drops out when I FOIL it out. 3 minus 6i. It's a fancy one, so 3 minus 6i also goes in the numerator. So now when I FOIL that, the imaginary part in the denominator should disappear. 3 times 3 is 9. 3 times -6i is -18i. 6i times 3 is positive 18i. The O and the I disappeared, which is great. And then I have 6i times -6i, which is -36i squared, which becomes positive 36. In the numerator, I have to distribute. 2i times 3 is 6i. 2i times -6i is -12i squared. Then we simplify that. The 6i I can't do anything with right now. The -12i squared becomes positive 12 over 9 plus 36. The denominator can be combined, 45. The numerator is written in the wrong order, so I'm going to write 12 plus 6i. We want it to be written in this format right here, a plus bi. So I'm going to split that into two separate numbers, 12 over 45 plus 6 over 45i. Then I can reduce those fractions. 12 45ths, I have a common factor of 3, reduces down to 4 15ths, plus 6 45ths also has a common factor of 3, reduces down to 2 15ths I. It's a coincidence that they both reduce to 15ths. Sometimes they'll reduce, sometimes they won't reduce. Sometimes one will reduce and the other one won't. Okay? But we do want them written as two separate fractions, just like this format right here. Now take a look at these two problems. The first one, we had one term in the denominator, only had to multiply the top and the bottom by I. On this one, we had two terms in the denominator. We had to wind up with complex conjugates here so we could FOIL to get rid of that I. On this one, same thing's going to have to happen, complex conjugates. On this one, same thing's going to have to happen, complex conjugates. And we'll deal with that next time.